Let's answer part A. Here we are given that h is constant and r varies with time. So I'm going to consider h as constant, and this means pi is also constant. I can rewrite this equation as v equals pi h times r squared. Now let's find the derivative of v with respect to time. So the derivative of v with respect to time, we can write this as dv over dt, and this equals, since these two are constant, when we use the constant multiple rule, we just put this constant as it is, and we find the derivative of r squared with respect to time. So first we have to apply the power rule here to find the derivative of r squared, which is 2r, and then we apply the chain rule to apply the to find the derivative of r, which is dr over dt. So I put this dr over dt. Now we can simplify this. Therefore, we get dv over dt, and this equals, I can put this as 2 pi r h times dr over dt. And so this is the answer for part A. So I'm going to write dv by dt equals 2 pi r h times dr by dt. Let's answer part B. Here r is constant and h varies with the time. So since r is constant, we can consider this quantity as constant. So therefore, we rewrite this volume equation as pi r squared. This is a constant times h. So let's find this derivative. That is dv by dt is the derivative of v with respect to time, and this equals, once again we use the constant multiple rule. So we put the constant as it is and find the derivative of h with respect to time, which is dh over dt. So this is how the volume is related when r is constant and h varies with time. So I'm going to write down the answer for part B, that is pi r squared times dh over dt. Let's answer part C. Here, both h and r vary with the time, and we have to determine dv by dt. So let's find dv by dt. So differentiate v with respect to time, we get dv by dt, and this equals, since both r and h varies with constant, here we have to use the product rule of differentiation. So first, let me consider this expression as first, and this h as second. So we can find this derivative when we apply the product rule. So in product rule, we find the derivative of the first, that is pi r squared. We find its derivative, multiply with the second, which is h, plus, now we put the first as it is, that is pi r squared, and then find the derivative of the second, that is h prime. So let's expand this. So we get dv over dt, and this equals, we find the derivative of pi r squared. Pi is a constant and the derivative of r squared is 2r, and then applying the chain rule we get dr over dt, and this has to be multiplied with the h, plus, now we find the derivative of this expression, that is for h prime we get pi r squared multiplied with the derivative of h prime, which is dh over dt. So let's put this in simplified form. We get dv by dt, and this equals, I have pi times 2r as well as multiplied with h. So I can put this as 2 pi r h multiplied with dr over dt, plus here I have pi r squared times dh over dt. And so this is dv by dt. In fact, we can write this in a simplified form, that is dv by dt, and this equals, we can factor out pi r from both terms. So I'm going to factor pi r, and when I do that, I'll be left with 2h times dr over dt, plus here I factor the pi r, so I will have r times dh over dt. And so this answers part C. That is, this is how volume is related to both R and H, or dr over dt and dh over dt, when both R and H varies with time. Let's answer question 6. In this question, we are given that water is pouring into the right circular cylinder whose radius is 6 feet and height is 11 feet. And it is pouring at the rate of 6 feet per cube per minute. And we have to determine the rate of change of height of the water when the depth is 9 feet. So let's see how to determine this rate of change of height. For this, I'm going to first write down the volume formula for the right circular cylinder, which is V equals pi r square h, where V represents the volume of the swimming pool, which is in the shape of a right circular cylinder. Now let me find the derivative on both sides. This is dV over dt. And notice that the radius of the swimming pool remains constant throughout. So we say that the radius is constant. That means we can put this pi r square as it is, and then multiply with the derivative of h, which is dh over dt. So basically, we have to determine this quantity dh over dt, which gives the rate of change of height of the water. So we solve for dh over dt. We are given that dV over dt is 6 feet cube per minute. So plug in dV by dt equals 6. So therefore this becomes 6. And pi times of radius is given as 6. So this becomes pi times of 6 squared times dH over dt. So first we divide by pi times of 6 squared. We get dH over dt. I write this in the form as dH over dt, and this equals, see that we can cancel this 6 with the power of 6. This becomes 6 power 1. So therefore it is 1 over 6 pi. This is 1 over 6 pi. We plug this expression into the calculator, and when we do that, we get approximately 0.053, and the unit of this is feet per minute, since this determines the rate at which the height is changing. So this is the rate of change of height of the water when the depth is 9 feet. Let's answer question 7. So here we have to determine dx by dt when x equal to negative 3. So let's use this equation xy equals negative 2. Here we have to do the implicit differentiation. So I'm going to use the product rule here. So consider the x as the first term and y as the second term. The derivative of x with respect to time is dx over dt times the second term, which is y, plus now we put the first term and multiply with the derivative of y with respect to time, that is dy over dt, and this equals the derivative of negative 2 is 0. Now let's put the values which is given. We know that the dy by dt is negative 1. So we can plug in for dy by dt, and x is also given as negative 3. And we can also find we can also plug in for x equal to negative 3. But since y is not given specifically, however, we can determine y by plugging in x equal to negative 3 into the given equation. So when we do that, we get negative 3 times of y, and this equals negative 2. So therefore we get y equals negative 2 divided by negative 3, and this equals 2 thirds. So y equals 2 thirds when x equal to negative 3, and this means we can also plug in for y. So we can easily solve for dx over dt. So let's plug in the values. I put or I write this dx over dt as it is, multiply with y, which is 2 thirds, plus x, which is negative 3, times of dy by dt, which is negative 1. So I plug in negative 1 for this, and this equals 0. So this simplifies to dx over dt, 2 thirds of dx over dt, plus negative 3 times negative 1 is positive 3, and this equals 0. So let's solve for this is dx over dt, small dx over dx. Solve for dx over dt by subtracting 3 from both sides and then dividing by 2 thirds. And this equals negative 3 multiplied with the reciprocal of the denominator fraction, which is 3 half, and this equals negative 9 half. So we found dx over dt equals 4 dx over dt, and this equals negative 9 half.